Okay, good morning, everybody. Thank you for joining us for our webinar of Who Puts Fluids in Data Centers. My name is Matt Husty. I'm an account executive here at Applied Flow Technology, based in the Houston, Texas area. And with me, I've got Liam Young, who's one of our sales engineers, who's located at our headquarters in Colorado Springs, Colorado. So just to get started, we're going to have a quick overview of who AFT is, some of our products, and we're going to go into where AFT fits in data center design. We're also going to do a brief introduction to one of our case studies, and then Liam's going to do a demonstration of a model that he's built of a data center with AFT Fathom. So AFT as a company has been around for over 30 years. We've got customers that range within 113 countries on the planet. We handle everything domestically here out of our headquarters in Colorado Springs, but globally, we've got over 32 distribution channel partners that we work with that help our customers internationally. We've also got over 100 universities that we work with that use our tools in higher learning in different engineering disciplines across them. So as you can see here, it's a snapshot of some of the industries that we work within. You can see from data centers to pharmaceutical, aerospace, technology, oil and gas, chemical, pretty much anywhere that there's fluid flowing through any sort of pipe or duct, that's where our tools can be implemented. And you can run models of those systems for various things that you're trying to solve for. In these industries that we work within, these are another snapshot of just some of the customers that we work with. As you can see, there's some large EPCs, some technology companies, again, aerospace, pharmaceutical, oil and gas. So it's kind of a wide range of people that we work with. It's been very interesting with me working with this company and being able to work in different industries and see different problems that people have and how they're solving them. Looking at our products, so there's 4 main products from AFT. Fathom, Aero, Impulse, and Extreme. We kind of separate everything out from whether it's going to be working with incompressible fluids or compressible fluids. And then are you solving for steady state issues, or are you looking at transients? So Fathom and Aero are what we work with steady state. And then for transients, our solvers are Impulse and Extreme. Again, Fathom and Impulse looking at incompressible liquids, compressibles, so gases, air, that's all going to be in the Aero and Extreme. We do have add-on modules that you can use within our tools, extended time simulation, goal seeking control, pulsation frequency analysis, and settling slurries. There's more information about these tools on our website. There's also videos on uses of some of these tools and different case studies and other webinars that we've done. You can find all of that information on our YouTube channel. So specifically today, we're looking at how do we analyze, optimize, and maintain efficient cooling systems. So AFT software provides tools to help design airflow, heat distribution, and pressure differentials within cooling systems. And that's what we're looking at here today when we're talking about data centers. So with this, we're looking at cooling water design and optimization, not only from the thermal aspect, but as in what different scenarios can you run of models to see from a cost effectiveness, the size of the components that you're using within your system, also the energy efficiency. So we know that energy has become something that's a hot topic within this industry because the more data that you're processing, the bigger that these data centers are getting, the power that's going into that obviously creates more heat. What do you do with the heat? How are you doing your thermal analysis? We have some components for compliance and reporting as well, building out reports for regulatory and industry standards, as well as proving out to end customers the engineering concepts behind what you've designed and what they're planning on building to ensure that they're going to run efficiently. And then from a scalability aspect, one of the things that our customers love is the ability to build smaller systems within a model, but then take those smaller systems and build it into a larger network. So you can do an analysis on a smaller system. You can run that same analysis whenever you build that larger network out with the capability to efficiently move through and make changes within the system as your design changes or as something comes in from your customers and how this is working. So there's two different common models that we look at whenever we're looking at data centers. We're looking at liquid air heat exchangers, and we're also looking at cooling towers. Everything's, again, having to do with all of the power that's coming in, the heat that's being generated, where is that heat going, and how can it work the most efficiently from an actual thermodynamic process, but as well as making it a cost-effective analysis. So that's what we're looking at here. Liam's going to get into a model later where he's built a chiller out, he's built cooling towers, and he's going to show you how that system works. So the case study that we're going to look at today is one that came in from one of our customers. It's a very large system that was put together with over 1,000 pipes and components. What they were working on was an evaluation of an 11-story data center. Had 9 HVAC circuits that they had some surge concerns on. So if there was a surge event, what was going to happen? They took a model they'd built out in Navisworks, imported that into AFT Impulse. They ran the steady state model to make sure that everything was going to work properly. And then they went forward and evaluated the surge concerns throughout the system. So then they took that evaluation, they took the information that they learned through the surge events that they thought were possible. What was that going to do? What was the effect going to be on the pipes? They took that information, gave it to their stress engineers so that they could do an evaluation. So the purpose of doing this was not only to ensure better operation and performance of the system, but also to mitigate concerns and risks when looking at financial losses that they'd be seeing through destruction of the property, any downtime, because we know that there's contractual obligations to end users on uptime for these types of facilities. So it was just making sure that the system was going to work properly, the cooling system was going to function as designed. If there was a problem, that it was all of the risks were mitigated within the system. So if we look at the model that they built, on the left, you can see in Navisworks, it's a fairly complex model. On the right is what you see was imported and how it got into AFT Impulse and what it looked like within that system. As you can see here, complex system, 11 stories, multiple HVAC units that were put into this. And then again, like I said, breaking it down into smaller systems, running analysis on smaller systems, and then building that into a larger network, running the analysis from that system to make sure that, yes, it's going to work from a smaller scale, but whenever you build it out, you scale it out to that larger network, ensuring that the system is going to function properly. And if there are issues, that you've built in the mitigations that you need to ensure that there's not going to be any issues with the system. So I'm going to take it now. I'm going to hand it over to Liam, let him walk you through AFT Fathom, a model that he's built. We'll go through his model. He'll do some discussion, and at the end, we'll have some questions and answers.
All right, thank you, Matt. So here I have built out a data center for this webinar. What I kind of wanted to start with was a little bit of the story behind building this model, because I feel like the kind of story of this might resonate a little bit. But when I first started designing this model, I was doing a lot of just over a napkin hand calculation type stuff. Just trying to put in some numbers. So I put in like 80 gallons per minute on the control valves. Um, uh, just trying to get overall ideas of like flow demands for the systems. And I thought I had a good design in my head. I started building out the piping and everything for this model file. And I went to hit run model on my first attempt and was immediately met with like 100 different error messages, letting me know that my initial design wasn't nearly feasible enough. Um, the mistakes I had made were one, I had just counted the flow to each of these air handling units, and then did the sum of all of that flow and just plugged it into the pump. But that's not actually how distribution of flow works in the system. You need a little bit of extra flow as it splits the different resistances in the system. So I actually had to bump up my flow in my pump to get all of those control valves to be able to satisfy their operating points. So that was what was causing a majority of the problems in the model, was just that single missized pump, basically. Um, but with that kind of story out of the way, uh, let's walk through kind of what this model's doing. So it kind of starts up at this top portion here, where I have built out a sort of cooling tower, where we're pulling in the water off of the cooling tower at about 80 degrees Fahrenheit, running it down to a chiller here at the bottom, which is cooling it down to about 40 degrees in this line. And then that's what's feeding the cold side of this data center. The flow is being distributed to a whole bunch of different units. Um, Originally, I said air handling units. Technically speaking, this setup would be able to work for both like air handling units, or if you were doing something more like a direct chip cooling, you could model these as individual racks um, for the flow coming into them, dissipating the heat and pulling it out the other side, effectively treating those servers as heat exchangers. So the cold water goes in through the loops and then comes out to this hot side. Um, and then feeds back in to that chiller again, taking off the rest of the heat from this original cooling and pumping that all the way back up to uh, the cooling tower, where it then sprays out the hot liquid to uh, kind of let the air cool it. So uh, the the next thing that I had found after I had built out the model, I had solved the issue of the flow rate coming through this model. Um, I had started doing a couple of design considerations. One of the big ones was what happens if I have excess flow coming off of this pump? This was actually a really interesting problem because each of these have a flow demand coming off of them. Um, and if I were to have excess flow, where does it go in the system? Well, technically speaking, this control system should just push my pump back on its curve until it's a balanced solution. But I didn't really like that sort of solution. It would mean having my pump potentially operate way too far back on its curve, which can cause efficiency problems, have your pumps break down more frequently, downtime on the cooling system, those sorts of problems. So in order to mitigate that, I also added this line connecting the remaining flow that makes it past all the heat exchangers back into the line. There's kind of two advantages of that, which was one, you can have more stable pump operations, and two, you're also looping back in some of the cooling water that you've already cooled back into your hot line, so the chiller doesn't need to do as much work at the bottom. Um, so with that, we can hop into results. Let's see. So parts of interest in this model, this pump, uh, I have delivering 10,000 gallons per minute throughout the system. And it was in a sizing mode, so it gives me some information about different line, the size of pump that I would need in order to satisfy the system. So it needed to add about 530 feet of head, operating at this 10,000 gallons per minute. There's a power estimation for it to have been able to do that, as well as it was showcasing for me my NPSHA. Um, Whether there's a pump that can actually do that is potentially questionable, but I'm certain there's a system of pumps that could satisfy this. So this would be something that I could maybe take to a manufacturer and work with them to get the proper designs that I would need for my systems. We can also check some of these heat transfer results, so you can kind of see in the various heat exchangers, we kind of have that cold water coming at roughly 40 degrees, and then each of the heat exchangers is um, adding what appears to be about 90 degrees worth of heat to the fluid. The working fluid in this model is just plain water. So you could also do a water glycol mixture if you wanted to, or some other working fluid. But just for the reference there. Um, the tool ends up being very flexible when it comes to doing a lot of these sorts of analysis to better understand your system. So here we can see very large piping flow network distribution. And here I'm just trying to point out some of these things in tabulated data. That can be a very challenging thing to analyze a huge data center when trying to do these sorts of things. So what I've also built out was a couple of quick uh, mapping tools. for color maps on the workspace, which will allow me to uh, quickly check certain things. For instance, I did a maximum operating pressure check. So if I show this on the model file, it's color coding my pipes according to this gradient here, basically saying that my maximum operating pressure for the size and schedule of my line is 1000 psi. Uh, and so I wanted to highlight anything in red that gets near or exceeds that. This model was fairly low pressure throughout its running, so I never needed to worry about that, which is a good thing because in a lot of data centers, if you're getting close to that max operating pressure, um, you're putting a lot of stress on like your flanges. It can cause more frequent leaks in the system, which in a data center is a big no-no. The other one that I had set up was a temperature distribution. This just gives me a little bit more insight into what's going on heat-wise in the system. So you can see we have that cold, relatively cool water coming off of the cooling tower, which gets further chilled. It then feeds into the loop, where when it passes by the heat exchanger, fluid gets fairly hot. But then we have excess flow coming through. Um, that's mixing with that extra hot flow to give it a more cool equilibrium temperature. And then that gets passed back into uh, the chiller unit, which is then putting more heat in and finally dissipating it all at that cooling tower. So, last couple of things that I wanted to just highlight in this model. Um, there's a lot of cool system design graphics you can make. My favorite thing in this model is profile graphs. So I can quickly just select a line. Uh, let's just check the. I can click. So here I'm just selecting a flow path to make a profile graph, just to kind of show a little bit of what's actually happening in the line of this. So here I've selected my flow path. I click this workspace button. We'll select from the list the pipes that I want to be using. And then I can simply generate a graphic here. So what we're seeing is we have a pressure loss as the water comes off the cooling tower, and then a pump that's adding a fair bit of pressure. Um, we then are moving through a flow split, which I believe is dropping the static pressure here. Where then at J99, it's J80, we're having a flow split off coming into um, this air handling unit. So what we end up seeing is a pressure increase as we shrink down the pipe. So we kind of went from expansions branching flow to a necking of the fluid. And then finally hitting that control valve to give us a pressure drop, then the heat exchanger after that. So what we can see in some of those weird pressure drop areas where we're kind of like, hey, why is there pressure rise here? Why is there pressure drop? We can better see that with something like a stacked graph. So here I am doing a stacked graph of velocity versus uh, static pressure. And so you can see here that in that first line, there is no velocity change, but then we changed the diameter of our piping, which is going to cause an increase in velocity. When there's an increase in velocity, there's a decrease in static pressure. And then here we have a decrease in velocity, which is going to result in an increase in static pressure. So those sorts of maybe weird trade-offs that you weren't expecting in losing pressure throughout the system are more easily explained when you can see something maybe like this. We could also maybe check how like overlaying plots works. So here, I could maybe do like an elevation versus hydraulic grade line. If I stack these two graphs on top of each other, it'll tell me if I have any sort of vacuum conditions. Um, so here, the elevation stays very flat. Um, but it looks like we do have a point where our elevation is above our hydraulic grade line. So we're actually pulling a little bit of vacuum. Um, on this upstream side. So you are very quickly able to glean a whole bunch of different insights from the model using various graphing tools. You're able to build out large networks of models in these tools. And you can quickly build out various different scenarios as well. So here we have our scenario manager. So I can make system design changes quick and easily. This scenario here would be my base scenario, but maybe I want to see like, I don't know, fouled heat exchanger. So if I wanted to maybe test the system's been operating for a while, things may not be operating at their best points anymore. Heat exchangers are getting um, corroded over time. You could make a change here, for instance, if I change this to maybe 0.8 on the heat transfer, then this heat exchanger will directly multiply on top of this thermal data uh, and not pull as much heat into the system. You can also do a whole bunch of those sorts of design factors on pipe frictions, fittings frictions, various different objects throughout the workspace, and quickly test out a scenario where that's true. So if I were to make this change, I could do this single heat exchanger, putting it out at 0.8. Let's just check the number on that. That's 2064. If I hit run, it takes about 8 seconds to run, I believe. It's going a little bit longer. Yeah. So here I can check that heat exchanger now. Oops. So you can see change the heat transfer a little bit in there. 0.8, 2064. So we can then see just off of that 80% efficiency, it's not dissipating as much heat anymore, not heating the fluid up nearly as much. So you could quickly test different design considerations throughout your model files, be very flexible with this. I think that covers most of what I had uh, for this model file. If there's any questions, I'll start fielding those now. So the first one comes from Victor with where our webinar recordings posted. I believe they will be posted to the YouTube channel. Should just be AFT YouTube channel. Then how seamless is BMI import to AFT? How much post-processing did it take in AFT? When we tried it with real life project, it took a lot of post-processing and wasn't feasible. Yeah. So the importing tools tend to be can be very challenging to use. It depends on how much data is retained in the model, what importing tool you're working with. Um, so for instance, I'm most familiar with like a GIS import. There you have to build out separate nodes and separate pipings, and then you have to stack them on there, and you have to let Fathom know what data you have inside of the GIS model. Um, and then what imported values uh, you're going to want to pull in from that model. Um, so it is fairly involved. A lot of times it'll give you quick line sizes, elevations. Um, so it's like diameters, lengths, and elevations. But you'll have to build out a lot more of the objects. The real time saver there is more so that you don't have to draw the layout itself. Whereas if you were to draw it by hand normally, um, you would have to draw every single individual pipe, specify every piece of data. So just by doing the import, it saves you the initial layout and the initial like pipe lengths and elevations. But there's still a fair bit of model building that might have to take place, like placing heat exchangers, um, uh, bends, fittings, valvings, control valves, those sorts of things may still have to be placed and built out. So it's kind of like the idea of it would have taken you a long time to do the initial model building, and the import's just trying to get you part of the way through that. So yeah, I can definitely see when you're trying to do it on a real life project how that could be very time consuming. So Christian Hurd, can you analyze a chiller failure and see how long a thermal storage tank will provide ride through until you can recover from a chiller recovery? So this is getting into transient thermal analysis. Unfortunately, we are only a steady state heat transfer analysis tool. So uh, you could maybe do a series of steady state scenarios with fairly large steps through them to get an idea of what the heat rate is um, at each of the situations you're in. And then maybe get an approximation based on that. But it'd be a very rough cut, and there's a lot of things that wouldn't be accounted for with that analysis. So um, that'd be there. Would it be possible to know the pressure reducing valves are set? So I'm assuming in the um, what the question is referring to is does it know where the operating condition is for those valves? So all the control valves in the system do have a set point that's a resistance. So we're actually finding the coefficient of resistance that's doing that. So whether that's a CV or a K factor, um, it is calculating that factor. And then if you wanted to, you could put in open percent versus loss factor data into those junctions, and it will report the open percentage of that control valve back to you. Uh, Next question is, I have a lot of trouble adding things to layers and control them in Fathom 13. Can you explain how to control the system on the layer side? So this one I will actually do in the model file itself. So layers. The way that layers works is they act like Photoshop layers. So you can add layers on top of what's happening in the workspace. So here I'm going to start by making a blank layer, um, which I will call heat exchanger temperature. So this blank layer has no data at all fixed inside of it. So if I were to hide this base layer, you could see my entire model disappear because this layer is blank. So when you're looking at this menu, what you're actually seeing is what you want to be visible on this layer. So for instance, I want these heat exchangers to be visible on the layer. And now when I hit this hide base layer, what we'll see is those heat exchangers that I selected in this layer are the ones that are showing. So what this means now is that I can start doing uh, different layers. So for instance, here we have heat exchanger parameters. So I can maybe do like temperature inlet and temperature outlet. And because the only thing showing on this layer are those few heat exchangers, um, it means that just for these heat exchangers, I'll have that temperature inlet and outlet appearing um, on those specifically. So I could do that for all the heat exchangers if I wanted to make them all visible with that temperature inlet and outlet. And so you can see here those popping out. So this is kind of the general functionality. If I wanted to hide these labels, I can hide them with this eyeball icon. And then the last thing is this pencil icon on the left here. This is telling me if I draw a new object on the workspace, do I want it to be shown on this layer or not? So the answer to this is probably no for this layer, but yes for the all objects layer. So I would want to keep that pencil icon off. Um, and then for everything else, the pipe parameters work exactly the same. You can just select the parameters you want to be showing on the workspace. Um, and you can select which specific objects you want to be showing at any given time. I hope that helps at least a little bit with the workspace layers. Um, more questions. Does Fathom have any built-in functionality to help determine the index run on a system? When you say the index run on a system, I'm assuming that's referring to runtime. Um, Not really. It's a series of several different, like basically for loops. Um, so because it's doing a Newton-Raphson method, um, it's going to be chaotic in terms of its solution. So there isn't necessarily a predicting of runtime. Um, that can be done for Fathom. If you're looking at like Impulse and Extreme, uh, we can take an estimated runtime based on a steady state run, and then the number of time steps that the solver is going to do to get somewhat of a time estimate. Um, but for Fathom runs, I will say if your system is taking more than about 15 minutes, I think is the maximum I've ever seen a model run for. And that was at about 2 to 3,000 pipes in the system. So if you're running longer than that, it usually means you're having some sort of convergence issue. I'd recommend reaching out to our support team to get help with that. Can NPSH analysis be conducted? So you can, depending on what you mean by an NPSH analysis, um, we calculate the available head in your system, and then if you place the required head inside of your pump object in the menu, then we will compare them against each other and let you know if your pump is going to cavitate. And then how many coolants are in the AFT database and can mixtures be created? So mixtures can be created if you're doing pure fluid mixtures, so like water glycol is possible. You can do that um, with, I believe, specifically for water glycol requires the Chempack fluid database. Um, uh, so you can do water glycol. Uh, in terms of the number of coolants, coolants tend to be very custom in their application. So I don't think there are too many coolants directly in Fathom, but you can add them as a user library fluid. And hopefully you can get in contact with the person who makes the coolant to get some of the fluid properties so that you can better model the system. Can you share your contact information? Yeah. I'll message that one. Um,
Liam, I've got the screen up. It's got the AFT website. It's got the call-in number for the office in Colorado Springs. I've also got my contact information that's up. You can reach out to me. I can put you in touch with Liam.
yep, that sounds perfect. Then next question, have you implemented flow balancing valves across parallel piped systems? For example, you set desired flow at each coil and have Fathom auto-calculate each balancing valve pressure drop to automatically balance systems. Um, so that gets into a lot of complicated modeling. Um, that might be better answered in like a separate message with a separate model to get a better understanding of what needs to be done there. But you can specify specific flows in pipes. You can put up bypasses. Uh, if it's just the base software, the control valves are self-actuating control valves. So you have to put a set point into the control valve for it to vary the resistance and find the solution. But if you wanted to do something that's more trying to do like a differential pressure across the two, or maybe like a temperature control valve for your system, that would be better suited for the goal seeking control module. Um, in that way, you can vary the resistance as your variable for the goal seek, and you can set various different goals like differential pressures, targeted temperatures, um, and have that solve automatically for that system. So the heat exchanger moves to this layer. It's more like there's a copy, a visual copy on the workspace of the heat exchanger on this layer. And so you can stack an infinite number of layers and you'll just have it, you can have an infinite number of copies of the heat exchanger stacked on top of each other. Um, again, it's purely visual, so the math is always going to be what's in the actual form that you double click into. Um, but the layers are just giving you extra visuals, stacking things on top of each other, so you can show and hide what's on each of those layers. Uh, for connections or accessories, it is preferable to use T-type accessories rather than nodes. Sometimes I like to use T's just to have the flexibility of the detail T model. It does some automatic pressure drop calculations. Um, so branches are considered lossless. So if you do a branch flow, it'll work the same. A, a regular T and a branch, sorry, simple T and a branch will have the exact same behavior in the system. Um, the T's just allow me to have flexibility to do some extra pressure drop calculations, which is why I like to use them when I have a 3-point connection rather than the branch. But you can also specify losses into the branch. So there's trade-offs to using each of them. Apologies, index run. Pipe run with most pressure loss, i.e. in your example, likely the air handling units the furthest away from your pump. Gotcha. So this to me is sounding similar to um like a critical path type of situation for the index run. Um, we don't necessarily identify which route is causing the path of highest uh, pressure drop in the system. Uh, what you can do, the pump and sizing mode in the model file is letting you know what the pressure drop, the total pressure drop down the critical path is going to be. Um, so depending on what information you're trying to grab off of the critical path, there's various different outputs throughout the system that can inform you of um, that exact, yeah, what the pressure drop is down that line. Um, you can also get you can also identify it pretty quickly just by which path tends to have the least flow. The path of least flow has the most resistance and therefore um, is there. Then I have a general question. Is it possible to schedule a web conference about the NFPA module? If we want, we could try. Yes, I think the simple answer is we have our support team. If you have um, if you reach out to any of the people on our support team or your local channel partner for support, we do set up meetings with customers to help answer questions about those sorts of things. If you want to set up a meeting with me to sit down, discuss how the NFPA module works, how to get all that up and running, be happy to. Um, So yeah, just feel free to reach out to Matt if you want to schedule something with me or support at aft.com is our general support inbox if you just want to get that question meeting set up and the question answered from them. And that looks like all of the questions.
Great. Well, thank you everybody for attending. Appreciate everybody being here. Again, my contact information is on here as well as the our website, as well as the phone number to our office headquarters there in Colorado Springs. If you have any additional questions or if anything comes up, please feel free to reach out to me directly. I can get you in touch with anybody in our group to help answer those questions and make sure that we get everything covered for you. If there's anything else you guys need, please feel free to reach out to us. Thank you again for attending the webinar. This will be up on our YouTube page with all of our other webinars if you want to revisit anything that you've seen here today. So thank you again. We'll see you guys on the next one.